We have two charges in free space. Charge Q1 is at the point P1. Now the x and z values are 0, so P1 is a point on the y-axis. The charge at point P1 is plus 10 nanocoulombs. 1 nanocoulomb is 1 billionth of a coulomb. So in coulombs, charge Q1 is plus 10 by 10 to the minus 9 coulombs. We have a second charge Q2 at the point P2. Now this is a point on the z-axis. The x and y values are 0. Its charge is plus 20 nanocoulombs, or plus 20 by 10 to the minus 9 coulombs. So we want the electric field due to both charges at the origin. Let's look at the electric field due to charge Q1 alone. Now we can call this electric field vector E1. Remember, E1 is the force on a unit positive charge, that is a charge of plus 1 coulombs located at the origin due to this charge here, Q1. Now this charge is positive. It's plus 10 nanocoulombs. So the force on a charge of plus 1 coulombs at the origin will have to be in this direction. It'll have to be a repulsive force, since like charges repel each other. Also, it'll have to be in a direction along the line joining the charge Q1 and unit positive charge at the origin. So here is Q1 in coulombs. I'm putting in the plus sign to emphasize that we have a positive charge here. Now what is this vector E1? Well, we can just go back to Coulomb's law. You know, the force between two charges is given by the product of the charges divided by the square of the distance between them. And we have this proportionality constant. Well, you know, Q2 could refer to this charge here. It's plus 1. So it's Q1 by plus 1. So basically, we just need this charge, which we can call Q1, and the distance r between them. Well, that's straightforward. You can see that the distance between them is 4 units. Now this is going to be a positive quantity because Q1 is positive. This charge here is positive. What about the direction? Well, this vector E1 points along the positive y-axis. So the unit vector along the positive y-axis is j. So we just have to stick a j after this. So this thing here is the magnitude, and multiplying by unit vector j gives us vector E1. Now let's look at the electric field at the origin due to charge Q2 alone. Well, it's going to be in this direction along the line joining the charge Q2 to the origin. We will call this vector E2. So, like before, we need to know the charge. Well, it's called Q2 here. It's 20 nanocoulombs. That's 20 by 10 to the minus 9 coulombs. And that's positive. It's plus 20 nanocoulombs. Divided by the distance between the charges squared. Well, the distance is 4, as you can see here. By the way, these units are assumed to be in meters. The SI unit of distance. So we have 4 squared here. Now, this is the magnitude of vector E2, but what's the direction? Well, this is the positive z-axis. You see, this is plus 4. So we're dealing with the negative z-axis. So unit vector in the direction of negative z-axis is minus k. So we multiply this by minus k. Capital K is the constant that we will plug in soon. To get the electric field at the origin due to both charges Q1 and Q2, we need to sum these two vectors. So you can see here, we can just complete a parallelogram. So this vector we will call E12. So, filling in for capital K, the constant remember is 1 over 4 pi epsilon 0. So epsilon 0 is 8.854 times 10 to the minus 12. So there's the charge Q1 on top. There's r squared, 4 squared, there's unit vector j. Over here, we have 20 nanocoulombs on top, 20 by 10 to the minus 9. The constant in front is 1 over 4 pi epsilon 0. R squared, the distance is 4, and we're unit vector minus k. So there is our vector E12. The j component is positive, the z component, or k component, is negative. Next, we want to place a third charge Q3 of plus 30 nanocoulombs in the YZ plane so that the electric field at 0 is 0. So we want to place a third charge Q3 somewhere that has an electric field like this, the same magnitude as vector E12, but in the opposite direction, so that when we add these two vectors together we get 0. So this is the vector due to charge Q3. We can call it E3. So here is vector E12 that you saw worked out, and E3 is got by minusing vector E12. Now Q3 is plus 30 nanocoulombs, so Q3 would have to be down here somewhere, because we want a repulsive force on a unit positive charge at the origin. Okay, here I'm just showing the picture again, but now I want to indicate the position vector of charge Q3. So this point is, say, A units along the y-axis and B units along the z-axis. So let's suppose the vector is AJ plus BK, and of course we have to determine what A and B are. A will be some positive number because we're dealing with the positive y-axis here. B will be a negative number because we're dealing with the negative z-axis here. Now the electric field at the origin due to Q3 depends on the distance from Q3 to the origin. Well, from Pythagoras that's going to be square root A squared plus B squared. As we saw in previous videos, the electric field at a point is a multiple of a unit vector for the charge responsible for the electric field to the point at which we are getting the electric field. So to get this unit vector, we notice that it's in the same direction as vector E3, but vector E3 is in a direction that's opposite to vector AG plus BK. So to get a vector opposite to AJ plus BK, that is this vector here, we have to minus this vector. So we stick a minus sign in front of AJ plus BK, and then we divide by the magnitude of this vector. Well, how do we get the magnitude? We just square the components, add them, and take the square root. That's from Pythagoras. So we're dealing with a vector that's in the direction of this vector here, from Q3 to the origin, which is opposite this vector, and it's a unit vector, so we need to scale down by the length of the vector, root A squared plus B squared. So that's this vector here. So from the previous video we saw that the electric field at this point is given by the constant 1 over 4 pi epsilon 0, it was referred to as capital K, times the charge responsible for the field in coulombs, which is plus 30 by 10 to the minus 9 coulombs, over the distance squared of the charge to the point we're interested in. So we have to square root A squared plus B squared, we get A squared plus B squared, and then we multiply that by a unit vector from the charge responsible for the electric field at O to the point O. So we multiply by this is our unit vector. We referred to it as R hat in previous video. So as a reminder, in the previous video the form was K times Q over R squared times R hat. So this is our R hat. So to find out what A and B are, we have to compare the J components. So we have to compare this to the J component here, which is actually all of this. So it's minus A over root A squared plus B squared times this quantity here. And of course the K components have to be the same. So the K component involves B over root A squared plus B squared, and of course this quantity here. So here we have 1 over 4 pi epsilon 0. We can multiply A squared plus B squared by A squared plus B squared to the power of a half, and that gives us A squared plus B squared to the power of 1.5. And as for the J component, we've minus A in front of it. Well, there's A, the minus sign has been taken out. Now 269.6 is the result of calculating this number here, 30 by 10 to the minus 9 over 4 pi times 8.854 times 10 to the minus 12. So that's going to give you plus 269.6, and then we have the minus sign from here. So that's the J component. and the j component must be equal to 5.617. So for the b component, we've b over a squared plus b squared to the power of 3 halves times this number here, which of course is 269.6, and we have the minus sign as well. So we equate the components, and we just do some rearranging here to get these fractions on their own. Now a convenient trick here is to square both of these equations and add the results. So we square this and add it on, and square this and add them together. Now if we square this, we get an a squared on top. If we square what's underneath, we get a squared plus b squared to the power of 3. To square the denominator, we just multiply 2 by the power. Similarly here, we get b squared over a squared plus b squared cubed. And if we add them together, the common denominator is a squared plus b squared cubed, and on top we have a squared plus b squared. Of course we have to do the same for the other sides. Square these two numbers and add them. Now we can cancel one of the a squared plus b squareds underneath, so we get 1 over a squared plus b squared all squared equals this number. And from that we can solve for a squared plus b squared. If we know what a squared plus b squared is, we can solve for a and b. We can just plug in 21.47 for a squared plus b squared in this equation to find a, and plug it in to the second equation to find b.